Good day po. Today I will discuss the exhaust gas recirculation or EGR. History of EGR. The first EGR systems were crude. Some were as simple as the orifice jet between the exhaust and intake tracks, which admitted exhaust to the intake track whenever the engine was running. Difficult starting, rough idling, reduced performance and lost fuel economy inevitably resulted. By 1973, an EGR valve controlled by manifold vacuum opened or closed to admit exhaust to the intake track only under certain conditions. Control systems grew more sophisticated as automakers gained experience. Volkswagen coolant controlled exhaust gas recirculation systems of 1973 exemplified this evolution. A coolant temperature sensor blocked vacuum to the EGR valve until the engine reached normal operating temperature. This prevented drivability problems due to unnecessary exhaust induction. NOx forms under elevated temperature conditions, generally not present with a cold engine. Moreover, the EGR valve was controlled in part by vacuum drawn from the carburetor's venturi, which allowed more precise constraints of EGR flow to only those engine load conditions under which NOx is likely to form. Later, back pressure transducers were added to the EGR valve control to further tailor EGR flow to engine load conditions. Most modern engines now need exhaust gas recirculation to meet NOx emission standards. However, recent innovations have led to the development of engines that do not require them. The 3.6 Chrysler Pentastar engine is one example that does not require EGR. The exhaust gas contains water vapor and carbon dioxide, which both have lower heat capacity ratio than air. Adding exhaust gas therefore reduces pressure and temperature during the acentropic compression in the cylinder, thereby lowering the adiabatic flame temperature. In a typical automotive spark-ignited engine, 5% to 15% of the exhaust gas is routed back to the intakes as EGR. The maximum quantity is limited by the need of the mixture to sustain a continuous flame front during the combustion event. Excessive EGR is purely setup application can cause misfires and partial burns. Although EGR does measurably slows combustion, this can largely be compensated for by advancing spark timing. The impact of EGR on engine efficiency largely depends on the specific engine design, and sometimes lead to a compromise between efficiency and NOx emissions. In certain types of situations, properly operating EGR can theoretically increase the efficiency of gasoline engines via several mechanisms. Reduced throttling losses. The additions of inert exhaust gas into the intake system means that for a given power output, the throttle plate must be opened further, resulting in increased inlet manifold pressure and reduced throttling losses. Reduced rejection. Lowered peak combustion temperatures not only reduces NOx formation, it also reduces the loss of thermal energy to combustion chamber surfaces, leaving more available for conversion to mechanical work during the expansion stroke. Reduce chemical dissociation. The lower peak temperatures result in more of the energy remaining as sensible energy near top dense center, rather than being bound up in the dissociation of combustion products. This affects the is minor compared to the first two. EGR is typically not employed at high loads because it would reduce peak power output. This is because it reduces the intake charge density, EGR is also omitted at idle because it would cause unstable combustion resulting in rough idle. Since the EGR system circulates a portion of exhaust gases, over time the bulb can become clogged with carbon deposits, which will prevent it from operating properly. Clogged EGR bulbs can sometimes be cleaned, but replacement is necessary if the bulb is faulty. EGR. In internal combustion engines, exhaust gas recirculation or EGR is a nitrogen oxide NOx emissions reduction technique used in petrol or gasoline, diesel engines, and some hydrogen engines. EGR works by recirculating a portion of an engine's exhaust gas back to the engine cylinders. The exhaust gas displaces atmospheric air and reduces uh, O2 in the combustion chamber. Reducing the amount of oxygen reduces the amount of fuel that can burn in the cylinder, thereby reducing peak in cylinder temperatures. The actual amount of recirculated exhaust gas varies with the engine operating parameters. In the combustion cylinder, NOx is produced by high temperature mixtures at atmospheric nitrogen and oxygen. This is usually occurs at cylinder peak pressure. In a spark ignition engine, an ancillary benefit of recirculating exhaust gases via external EGR valves is an increase in efficiency, as charge dilution allows a larger throttle position and reduces associated pumping losses. Mazda's turbocharged skyactiv direct injection gas uses engine uses recirculated and cooled exhaust gases to reduce combustion chamber temperatures, thereby permitting the engine to run at higher boost levels before the air-fuel mixture must be enriched to prevent engine knocking. In a gasoline engine, this inert exhaust displaces some amount of combustible charges in the cylinder, effectively reducing the quantity of charge available for combustion without affecting the air-fuel ratio. In a diesel engine, the exhaust gas replaces some of the excess oxygen in the pre-combustion mixture, because NOx forms primarily when a mixture of nitrogen and oxygen is subjected to high temperature. The lower combustion chamber temperatures caused by EGR reduces the amount of NOx that the combustion process generates. Gases reintroduced from EGR systems will also contain near equilibrium concentrations of NOx and CO. The small fraction initially within the combustion chamber inhibits the total net production of these and other pollutants when sampled on a time average. Chemical properties of different fuels limit how much EGR may be used. For example, the methanol is more tolerant to EGR than gasoline. In light-duty engines, the introduction of EGR technology to engine passenger cars in the 1990s went almost unnoticed and was not considered a major breakthrough for several reasons. Because the required NOx reduction was quiet modest. The system allowed little EGR back into the cylinder and there was no need for EGR cooling. Typical passenger cars engines operate mostly at fart load conditions where temperature are relatively low. It was only the Euro 3/4 legislation that created higher demands on EGR systems and triggered the introduction of increasingly more sophisticated, electronically controlled cooled EGR systems on light-duty engines. Heavy-duty engines. Heavy-duty application of EGR date back at least 1997 when the technology was used on some naturally aspirated engines, such as Caterpillar's 3208 to comply the California's 5G BHP-HR NOx plus HC limit for heavy-duty diesel engines. However, through the 1990s and 1980s, the use of EGR on heavy-duty engines remained limited. EGR was not required to meet regularity emissions standard, and the application of technology was driven primarily by incentives such as US EPA voluntary low emission vehicle certification program. The wide-scale launch of cooled EGR on heavy-duty engines that attracted a lot of attention to the technology took place in late 2000 in the North American market. This momentous introduction was in a part triggered by the consent decreases and the political upheaval that surrounded the issue of dual mapping that led to the 1998 settlement between the US EPA. Non-road engines. EGR technology was also adopted by non-road engines. Some of the first non-road application of cooled external EGR were in the US Tier 3 John Deere PowerTech Plus engines. The first cooled EGR John Deere engine was the 6-cylinder 9-liter model 6090, launched in 2006, followed by 6.8-liter and 13.5-liter models. These engines use high pressure loop cooled EGR and the variable geometry turbocharger. It is interesting to note that the 6090 EGR engine used in the John Deere 8000 series tractor in 2006 had the lowest fuel consumption of all time, demonstrating that the fuel economy penalty associated with EGR can be overcome by skillful engine design. Other application of cooled EGR for Tier 3 included Komatsu 11.0, 15.2, and 23.2-liter ECOT 3 engines and Diot's TDC 2012. Marine engines. Low-speed marine engine application of EGR are perhaps the most challenging technically. Prior to implementation of the IMO Global Sulfur Cap on marine fuel of 0.5%, these engines were designed to burn heavy fuel oil, HFO, that produces exhaust gas heavily laden with metals, sulfur, and other components that must remove before the exhaust gas is reintroduced into the engine. While EGR had been considered by some of the unsuitable for engines burning HFO because of the cleaning challenges by about 2010. All major manufacturers of low-speed marine engines were considering EGR for HFO IMO Tier 3 applications. MAN Diesel and Turbo announced commercial orders as early as 2011. Some application of the water treatment system for application burning fuel with less than 0.5% sulfur are possible. Future trends. Many advanced combustion concepts under development, for instance low temperature combustion, utilize very high EGR rates for emission control. This is likely to put even more demand on future EGR systems and their components if the application of LTC over a significant portion of the engine operating map becomes commercial. That's all. Thank you po.